In this video, we're going to do a brief overview of weak acid, strong base titrations and strong acid, weak base titrations. We're just going to take a look at the titration curve and briefly explain the logic behind it. And then in the following lesson, you're going to take a look at some calculations related to weak acid, strong base, and strong acid, weak base. So a weak acid, strong base titration, if we take a look at the titration curve, we're comparing it here to a strong acid, strong base. Here's a weak acid, strong base. You can see that the middle of the steep portion is just below the 8 mark. So the equivalence point for a titration like this, where you have a weak acid and a strong base, is a pH that's above 7. So for following what's happening, you start off with your weak acid in the flask. How do I know that? Because our pH starts off at less than 7. Then as you start to add some of your strong base, let's say it's NaOH, for example, the pH starts to rise. Slowly, of course, but it does start to rise. And again, similar reasons, you're adding some OH to a primarily acidic region. Now, this region in a weak acid, strong base titration, around here especially, and also in a strong acid, weak base titration, this is called a buffer region. And so what happens at that point is you get a region where the pH change is very slow. There's a resistance in pH change. And that's because what happens is you have your weak acid has set up an equilibrium with its conjugate base, and they've created what's called a buffer, where essentially it's a system that's set up in equilibrium to resist pH change. But eventually, as you continue adding beyond the buffer region, your pH will continue to increase until you get to this part where you essentially have reacted with most of your acid, and then you reach the equivalence point where all of your acid and base have reacted with each other. And then if you go beyond that, now you're overshot again. But the main point here is that in the case of a strong acid, strong base titration, the pH at equivalence is equal to 7. But in the case of a weak acid, strong base titration, the pH is slightly above 7. And the reason is that when you do this type of titration, you produce a basic salt. So just an example that you might see, suppose we have a weak acid, CH3COOH, and we make it react with some NaOH. So this is the weak acid. This is the strong base. When this reaction happens, you get a double displacement. You get CH3COONA, aqueous, plus some H2O. And so what you'll notice here is that you have a salt. The Na doesn't have an effect on the pH, but the CH3CO- does, because this is a salt of a weak acid, which acts as a weak base. So this is a weak base that was produced. And so that's why your pH is above 7 at the equivalence point. So you don't have to be neutral after a reaction between an acid and a base. That's only for strong acid, strong bases. For weak acid, strong bases, you produce a salt that has a weak base in it, and as a result, your pH is above 7. Now, let's take a look at the situation where you have a strong acid, weak base. So in here I have a strong acid, and over here I have a weak base. How do I know I have a strong acid in the flask? Well, I'm starting off by measuring the pH, and I can see that the pH is less than 7, pH of 2. And so, similar to what we saw in the strong base, weak acid situation, we start off with a pH 2, we slowly start to add some of the base, the pH starts to increase slowly, and there is a buffer region as well, where there's a bit of a slowdown in resisting to the change in pH because the weak base has set up an equilibrium with its conjugate acid, and they resist the pH change according to Le Chatelier's principle. And we'll see more detail on that later on. There's also an extra resource that you can go and read in the optional and additional lesson section. But again, there's a resistance to the pH change a little bit, so it's a slow increase. And that's really in the case of strong acids, weak bases, and strong bases, weak acids. But eventually we get to a point where we go beyond that buffer region, and we're almost done reacting with our acid, and we get into our steep region here. And so we're comparing this to a strong acid, strong base. Here we have a strong acid, weak base. The green line, the shorter line here, you'll notice that the middle of that steep portion is actually below 7. That's not really a straight line there, but below 7. So the pH at equivalence is actually less than 7 for a situation like this. So for strong acid, strong base, as we mentioned, is equal to 7. But for a strong acid, weak base, the pH at equivalence is actually less than 7. And so that's one of the key defining features there. Everything else is essentially the same. You have your overshoot region where you go above the equivalence point way too much. You have your region below and your buffer region, all that stuff. They're all the same. But the equivalence point is less than 7, and that's because the salt that's produced is actually a weak acid. So for example, let's say my strong acid was HCl, AQ, and I was using a weak base in my my situation here. So, or my titration. So let's say the weak base is NH3. So when I do this reaction, I actually get NH4Cl. And this is aqueous. The Cl has no effect on pH because it's Cl minus, salt of a strong acid. But this over here is a salt of a weak base. It actually acts as a weak acid. So we get an acidic salt, which is why the pH is less than 7. Now I know this reaction looks a little bit weird. In reality, when you have NH3 in a solution, you should actually write it like this: HClAQ plus NH4OH. AQ produces H2O liquid plus NH4ClAQ. It's the same thing. This is just kind of a shorthand way of doing it. Ammonia in a solution actually exists as ammonium hydroxide. But the main point here is that this here is a weak acid. It's an acidic salt, and that's why the pH is less than 7. So in grade 11, when you had a titration, if I asked you for the pH at equivalence, once the titration is over, you would say pH is equal to 7. You don't really have to do any calculations. It doesn't matter what the concentration of the salt is, as long as you do the titration correctly. But in grade 12, when I ask you what is the pH at equivalence for a weak acid, strong base titration or a strong acid, weak base titration, you will need to do calculations because, as we saw for the weak acid, strong base, it's going to be above 7, and we can actually figure out exactly where above 7 it will be. And for the strong acid, weak base, it's going to be below 7, and we can do some calculations to figure out where below 7 it will be. And so that'll be the next few lessons coming up: titrations of weak acid, strong base, and strong acid, weak base.